Hey, so we're gonna make the best out of a bad situation. We're starting our gas saws unit. We'll start those with a few demonstrations. I'm disappointed because this is one of the more fun things to do as a group, interactively and all that kind of stuff. But what we'll do is we'll do a video, and then we'll have a few questions on Moodle afterwards. As long as you watch the video, you should be able to do the questions on Moodle, no problem. So getting into a gas saws unit. So first kind of idea is, what's inside our burette here, right? So what's inside the burette? Well, we can look at evidence of that, right? We've got gases inside here. So as we push down here, I don't know how well you can see that. We can make use of another good word, diffusion. Right? Because if I put some food coloring in here, that food coloring will diffuse. Diffusion is random motion of molecules, right? So where there's areas of high concentration of green, it's going to move around to areas where there's low concentration of green, and that should make it a little easier for us to see what's going on there. I don't want to stir with a $45 burette. So this might make it a little easier to see. Right, but as we put this in here, the air pushes back, right? You can see the line that's in here. Now, the further down I go, the more that goes up into the burette, but the water can't go into the burette because there's air in the burette, and the air pushes, right? The air pushes quite a bit, actually. We just don't notice it because we're exposed to that all the time. But that air is pushing the water back. So, I don't know, can we see that very well? Yeah, you can kind of see that in there, right? So the air is pushing back. If I were to open the stopcock on the burette, right? So the stopcock on the burette is open now, and we put that in there. We can see the liquid goes right into the burette, right? So then once the air is allowed to escape, it can come back out. But, right, that air pressure pushes quite a bit, right? We can see that. Pressure is a big idea for us when it comes to gases, right? Because unlike solids and liquids, gases take the shape, well, liquids take the shape of their container, but gases fill up the entire space, and pressure is going to be a big deal for us. We're going to use pressure quite a bit. Now, when we look at pressure, the formula for pressure is force over unit area. So I'm going to apply some pressure to my balloon. I've got a bed of nails here, right? So you can see that bed of nails. I'm going to set a balloon down on here, and then I'm going to set a board on top of here, right? And we've managed to not pop the balloon with the board setting on here, but I can even, well, we're going to try. We're going to try and put some more weight on our balloon here, some more force, right? So take this, and we're going to put this on here. Oh, look at that. Not popping the balloon. Put some more force on it. Still not popping the balloon. Just continue to add some force to it. Right, so pressure is force per area. Okay, here we go. We're going to put a lot of weight on here. A lot of force, right? A lot of weight is a lot of force. Well, we're running out of weights. I don't know how many more weights I can fit on here. Right, I can even push it down some, right? So pressure is force per area. So with a bed of nails, it's like a common magician trick kind of thing, right? With a bed of nails, there's actually a pretty large area there, right? Each nail is pretty sharp, but there's a whole bunch of nails there. So when you put it over that whole area, I can push into this with a pretty good amount of force, and it doesn't hurt or anything, right? So magicians will lay down on these things and stuff. This is not big enough. I'm not going to lay down on it or anything. But there's a large area, so you take that same force, spread it out over a large area, and it's not that much pressure in each given spot, right? So the balloon doesn't pop. We'll look at a couple other pressure things. Move this stuff out of the way and move the computer so we can see what's going on here. Let's see. Move it like so, right? So let's see how well we can see that. So this is just a newspaper, right? Got a regular old newspaper, and I've got a board, nice, thick, sturdy board, right? And we're going to take So it seems to be cutting us off after 5 minutes. So I don't know if we're going to redo stuff or just have to do these shorter videos. But anyway, I got a regular newspaper here. I got a nice board here, right? Newspaper has a lot of square inches on it, right? So there is air from the atmosphere pushing down on all of this stuff, right? So if I want to push down on this board, that's going to lift this newspaper up, right? And there's quite a bit of air on top of us here. So if I do that in a quick fashion, right, we'll give that a try, right? I did that real fast, so the air was pushing down on it, but there's nothing pushing back up underneath. So, 14.7 pounds per square inch is what the atmosphere pushes on us. So if you imagine all the square inches here, that's a whole lot of force that it's got to be able to lift up. Now, if I do it slow, some air can get underneath there just fine. But if we do this fast, and I try and push most of the air out from underneath it, right? So I broke again, just kind of there. As this board gets shorter, it doesn't work quite as well because now it's not over, like it's only going back to here, right? So I don't know that we're really truly getting the whole newspaper here, but right, continues to break. Continues to break. At some point here, it's going to fail. Yep, that time it failed. It just ripped the newspaper right there, right? So, but the atmosphere provides a lot of force down on things. So it's doing the same thing on your hands, right? So it's doing the same thing on your hands. You can't see me. That's probably weird, right? So when you have the pressure on your hands, that's doing the same thing. But every square inch of your hands has 14.7 pounds per square inch pushing on that. Where did that go? Pause. So that 14.7 pounds per square inch, about 15 pounds per square inch. So you hold your hands out and you figure, well, they're at least 5 inches long and 2 inches wide, right? So if they're 5 inches long and 2 inches wide, that's 10 square inches. So that's 150 pounds pushing down on your hands. So then if I'm going like this, I'm doing like 300-pound curls right now, right? Isn't that what that would mean, right? We just saw that that's real pressure. So that must be 300-pound curls that we're doing right there. But it doesn't feel like so much. I think I would be much bigger and stronger if I could curl 300 pounds, right? So that brings us to another one that I'm sad that y'all aren't here because this is one of the more fun things that I get to do. But we're going to take this. I've got a little piece of transparency film here, and I've got a graduated cylinder with some of that green colored water in it. And what I'm going to do is I would like to walk around the room. And I tend to make some students nervous as we do this, right? And I'd find somebody like Leclerc or somebody that I like to pick on. And then we're going to go ahead and, see, the first time you got to hold it a little bit. Leclerc would have been upset if that had happened to him. But if we go over the top and do that, right? That's upside down, right? So students say, it's like suction, pulling it back up in. Well, suction doesn't exist. That's not a real thing. So this can't be suction. But that 14.7 pounds per square inch is pushing everywhere. Well, if there's water here, then that means that the air can't be pushing there, right? So it can hold on there pretty well. Once it gets a little bit of a seal, that very first time, tipping it over can be kind of tough. But I would have spilled a little bit on somebody there. But anyway, so 14.7 pounds per square inch pushes everywhere. So it does push on the top of your hand, but it also pushes on the bottom of your hand. So you're able to push when you do your curls like this, right? When you do this, yeah, it's pushing down on your hand, but it's also pushing on the bottom of your hand as well there, right? Let's see, which things haven't we done yet? Pause us here. Hey. All right, so let's take a look at some other stuff that we've got to figure out for gas law stuff. And the next one is a barometer, how a barometer would go about working. So what they do with a barometer, which baro means pressure, barometer then, right, is a pressure meter. That's a thing that we use to read the pressure. So some nice pictures of that in the textbook and stuff as you're going through and reading the chapter, which we need to read the chapter. I don't know, is it worse to not see the stuff or not see my face? This is just weird. But anyway, the way a barometer works is the air pressure pushes down on the surface of our liquid, and that pushes the liquid then up into the test tube. So what students will tend to want to say is that the water is like sucked up into the test tube, right? But there is no such thing as suction. That does not exist. What does exist is air pushing on things. So if the atmosphere pushes down on this and there's the weight of the atmosphere pushing down, then the weight of whatever the stuff is in here is going to push down. So you can think of it basically the atmosphere like having a weight. So if the weight of the atmosphere pushes down on this, then the weight of the water needs to balance that out. If we think back to physical science, if there is no net force, then there's no movement. So here there must be no net force difference so that they're balanced out. So this atmosphere weight can lift this up until you get a column that's going to weigh as much as the atmosphere does. So with mercury is really dense. That only takes 760 millimeters of mercury. With water is 13.6 times less dense. So it's like 32 feet, right? So that's how a straw works, right? You're going to make an area of low pressure in your mouth, and then the atmosphere pushes down on that. If you don't have access to the atmosphere, then a straw doesn't work, right? So you couldn't use a straw in space or whatever where there's no atmosphere. Well, I guess there is atmospheric pressure because you're inside the spaceship or you're dead. But anyway, we're going to go ahead and work a couple pressure conversions here. We've got a couple in your packet. So not a bad idea to pause this and try and work one or two of those ahead of me. If you're really lost and don't know what to do, just go ahead and work through the first couple with me. We'll make sure an answer key is posted for this. But anyway, so if we go to that 2A, number one, those are on the back of your periodic chart. What are the normal pressure units? Those are in the notes too. But PSI, pounds per square inch, is one of them. So 300 PSI. Equals how many torr. So if I want to do this is just a unit conversion. So I do 300 PSI here, and then we're going to say, well, we need PSI down here and torr up here. So if we look on the back of our periodic charts, we see the numbers there, and it's 14.7 PSI, that's the pounds per square inch, is going to be equal to 760 torr. Both of those amounts are the amount that is in our atmosphere, right? So that's how much you're walking around under 14.7 PSI all the time. You're walking around under 760 millimeters or torr or millimeters of mercury. Those are the same thing. So I put 14.7 on bottom. That is not even legible. 14.7 PSI on bottom, 760 torr on top. So then we multiply across the top, divide by the bottom. So 300 times 760 divided by 14.7, and that's going to give us 15,510 torr, which it looks like on the worksheet I only gave you one sig fig, so you'd round that to 20,000, right? But would be the best answer. But 15,500 torr is equivalent to 300 psi. We'll need to be able to convert back and forth between our pressure units when we're solving these problems. Looks like we've got enough time to do one more problem there. The second one there under 2B, 2.3 atmospheres. Atmospheres was a unit just kind of made up by chemists because it's convenient for a lot of things, right? So 2.3 atmospheres. One atmosphere is equal to 760 millimeters of mercury, which is what they were asking about, right? So the 760 millimeters of mercury, that's based on how a barometer works, right? The column of mercury that the atmosphere can hold up is 760 millimeters. So that's 76 centimeters. So what about this tall, right? So that column of mercury is equal to the atmosphere pressure. So 2.3 times 760, and that's going to give us 1,748 millimeters of mercury, or I can at least kind of do sig figs here. That'd give us 1,700 millimeters of mercury to 2 sig figs. Right? Yay, math is back, so we get to worry about sig figs and all that kind of stuff. Right? So that's how a barometer works. There's a nice picture on 240.